Go ahead.
Okay, so thank you for introducing me and welcome to the presentation about Micropython binding to LVGL in Zephyr operating system. My name is Zuzana Miklankova and I currently study at Faculty of Informatics at Masaryk University. I study there embedded hardware or embedded development. I am also a junior C++ developer. This year I was writing my master thesis with cooperation with the NXP Semiconductors, and the topic regards Zephyr operating system, Micropython and LVGL. The integrations and measurements which will be stated or mentioned in this presentation are sourced from this thesis which I was writing. So what was the motivation to create or integrate the Micropython binding to LVGL in Zephyr operating system? The motivation was to create a system for embedded developers, for them to be able to design and implement fully fledged graphical interface in their embedded devices, even after the compile time, so in runtime. Multiple features from multiple projects were joined together in this solution. The Zephyr operating system provided the hardware support, the interactive prompt, which is used for programming in the runtime, is provided by Micropython, and the graphical components are from the LVGL. Now I would like to briefly introduce a used project in this integration. First project which was used was Zephyr operating system. As you already probably know, it's a modular real-time operating system designed for constrained devices. Next project which was used is Micropython, and Micropython is implementation of Python 3 for constrained devices. Micropython on its own provides its hardware abstraction layer, so has its own drivers for some boards. LVGL is open source graphical library, is modular, so the user can choose which components will be built to the targeted binary. And also it's hardware independent, so user needs its own set of display and input drivers in order for LVGL to work. The last use project is LV bindings, and it's a project which binds Micropython with LVGL, so the LVGL functions can be called directly from the Micropython code and not from the C as usual. Okay, so at first, integration had to be done in order for the system to work. Some integrations between the project already existed before I started to write the thesis. For example, Micropython with Zephyr combination existed, and LV bindings, so Micropython with LVGL existed. I would like to mention used software versions of each of the projects, because the projects are in rapid development cycle and are changing a lot during the versions. So here they are stated. The hardware used during the integration and also then for the measurements is RT1050 evaluation board from NXP. Here is the picture of it with some LVGL graphical component displayed. So in order to integrate LVGL to any project, any C project, some steps need to be done. At first, the user has to configure the LVGL as he needs or she needs. This is done in LV configuration file. Entries like resolution or color depth or memory primitives can be configured here. When the configuration is done, in the main program or the main source file, the user had to call the LV initialization function, and this init function internally sets the LVGL to initialize state and has to be called before any other LVGL function. Then the display driver registration and input driver registration need to be done. Your hardware driver for your display and input have to be registered with LVGL, so it knows what driver to call. Then the LV task handler need to be called periodically during run of the program, and that's because the LVGL handles its internal task within the LV task handler. The tasks are, for example, read input task or animation task. Zephyr operating system already supports LVGL, as I already mentioned. The driver registration and initialization functions are available in libgui LVGL directory, and all LVGL sources are included in modules section in Zephyr codebase. The LVGL is initialized automatically during the Zephyr boot, and it is done with the sysinit macro, I think after the kernel starts, just after the kernel starts in the application phase. The LVGL is built with the resulting binary only if it is enabled in kconfig configuration in the Zephyr. Zephyr operating system provides hardware support, so it contains some display drivers and input drivers, which can be used by the LVGL. Here on the right side can be seen the resulting binary built with user application using the LVGL library and Zephyr operating kernel and hardware abstraction layer. Micropython with Zephyr operating system integration. So this combination also existed before I started writing the thesis. The Micropython project contains the Zephyr port as one of its targets, which can be built. And in the final binary, the Micropython is built as a Zephyr user application. Even though the Micropython has its own set of hardware drivers and hardware abstraction layer, in combination with Zephyr operating system, it uses the hardware support from Zephyr. The Micropython of version 1.14, which I have used in the integration and in the measurements, uses makefile system for building the Zephyr port, and these makefiles then call the Zephyr CMake internally. But recently the Micropython version 1.15 was released, and this release brought, for example, changing makefiles to CMake files. So currently the Micropython can be built with Zephyr operating system with the West tool provided by Zephyr with CMake system, same as other Zephyr files. Zephyr port is therefore still in development phase. As can be seen, the changes are big between the versions. And in the right side can be seen the resulting binary. Now the Zephyr operating system is still on the left, and on the right side as user application isn't the Micropython. The LV bindings. The LV bindings automatically generates or creates Micropython wrappings for LVGL functions and structures, and user has to choose which functions and structures will be wrapped and therefore can be used from MicroPython. And this is based on LV configuration file, same as the whole LVGL is configured from. The generated wrappings are then stored in a LVMPI-C file, and this file is integrated into MicroPython as its external C module, or thus then can be imported as from Python as a Python module. The LV Bindings project integrates its own set of hardware drivers, mostly for display and input. And also, same as a Zephyr operating system, the LV Bindings project contains all of the LVGL source files. The LV Micropython is forked MicroPython repository hosted on GitHub, which has some which have some integrated bindings already integrated, for example, for the users. Here on the right side can be seen the external C module for MicroPython, the LV bindings. Okay, so the integrations were mentioned till this moment already existed, and these are steps which had to be made by me in order to integrate the whole solution together. So here's some strategy. It's not the only one which could be used, but it's the one I used. And it's as follows. The LVGL sources were taken from LV Bindings project and not from Zephyr operating system. And that is because the LVGL as a part of MicroPython will be used as external C module to the MicroPython and not directly logically linked to the Zephyr operating system. The goal was to make no code adjustments in Zephyr operating system, and that is because the Zephyr port in MicroPython also contains changes only in MicroPython and not in Zephyr. Therefore, the Zephyr knows nothing about MicroPython. The Zephyr driver, the goal was to add the Zephyr driver in LV Bindings project so that the LV Bindings can use all drivers available from Zephyr hardware base in the bindings. And in order to build the proper binary together, the MicroPython build system had to be adapted. Goal was also to upstream the results if it is possible. So here are listed some integration details. Indeed, the Zephyr driver was created in LV Bindings projects. The core part of it was taken from Zephyr code base because the Zephyr already supported the LVGL. LVGL sources were taken from LV Bindings, but have to be checked out on the version which is currently used by the Zephyr operating system, and that is because the registration and initialization, the Zephyr driver is taken from the Zephyr codebase. Then the makefile and CMake files were adjusted. For example, the Zephyr kernel needed to be linked directly with MicroPython app because of the kernel queues which are used in input drivers in Zephyr. Changes were indeed upstream successfully in LV Bindings MicroPython and in LV MicroPython projects. And here is the picture of the resulting binary. It can be seen the MicroPython is as Zephyr user application containing the LVGL and LVGL bindings. Some profiling of most notable characteristics of the system were done. Characteristics as a binary size, heap consumption, stack consumption, or CPU execution time. And this was done because if to find out if Micropython layer add or need more resources than the system without the Micropython layer. So two kind of demo applications were written for the profiling. First kind of application is called Zephyr application, and it consists of LVGL application directly on the Zephyr operating system, and it's written in C language. The other kind of applications are called Zephyr with MPI application, and here the LVGL is set as an external C module on top of Micropython, on top of Zephyr operating system. And these applications are written in Micropython. LV configuration file were set equally for both types of application to maintain some objectivity, except for memory management primitives, because the LVGL about the Micropython uses memory primitives from Micropython. Kconfig for both types of binaries were also set almost the same, except for small things, for example, as logging system. All the binaries have been compiled with GCC and with size optimization enabled. So here are some results. First, the binary sizes comparison. On the right side on the graph can be seen 4 stages of application, with and without the Micropython layer. The first application contained only LVGL and driver initialization, and the fourth one contained LVGL, driver initialization, and all LVGL widgets initialized. The second and third application contain third and 2/3 of LVGL widgets initialized. Here can be seen that Zephyr with Micropython is significantly bigger. The binary size is bigger, but does not really grow with added LVGL widgets. And the reason can be that Micropython is interpreted language, and thus the compiler during the compile time does not know which widgets should compile in and which not, so it compiles all the widgets from the start. The heap size. The LVGL stores its widgets on the heap. So in the graph on the right side can be seen again application with Micropython layer and without Micropython layer. In the first measurement was taken after LVGL and drivers initialization. Second measurement was done after allocating 5 LVGL widgets, and the third measurement was done after allocating 10 LVGL widgets. It can be seen that Zephyr application with Micropython has higher consumption of the heap. The stack size, again on the graph can be seen measurements after the initialization, after 5 widgets were allocated and after 10 widgets are allocated. Here can be seen that there is not really a significant difference between the two types of binaries, but the Zephyr application without the Micropython layer has more or higher stack consumption, and it can be because the pointers to the LVGL widgets were stored in the array, and Micropython acts differently or behaves differently with arrays than the C language. Then the input delay was measured. The differences between two time marks were taken and then compared. First time mark were taken in the input driver when the input signal came to the device, and the second time mark was taken in an LVGL callback function, so when the LVGL source cores were called. The results are biased with the measurement tool. The measurement was taken with help of changing state of GPIOs, and then the changing state of GPIOs were analyzed with external signal analyzer. It can be seen that a Micropython layer adds about 1,000 microseconds to the input delay. And the last profiling, which can be seen in this presentation, is execution time. The demo application contains initialization of 2 full covered LVGL screens, and time measured was switching between the screens, from the screen 1 to the screen 2 and back to the screen 1. The graph shows us that there are no difference between the application with Micropython layer and without Micropython layer. So in the conclusion, the solution was integrated, it's functional, and can be cloned from GitHub. They are upstreamed successfully. The profiling showed us that the most relevant difference between binary with Micropython layer and without Micropython layer is in binary size and maybe also in the heap consumption, and that no other significant differences were present. Also, in the end, it's better probably to write applications in C when you aim for a small binary, and when you want to prototype fast some graphical units, you can use Micropython, which can be good for you. Here are some references of all projects which were used in this presentation, and also to the thesis which was sourced. Thank you for your attention, and that's all for me. Are there any questions, maybe? Okay, so I think there are no questions. So again, thank you for attention, and oh, I see something in the chat. Oh. Thank you. So, bye.
Thank you, Susanna. Good presentation. Congratulations too on your thesis.
Thanks. Bye.